Now we will start chapter 19, which is on numerical integration. And I think that some ideas of this chapter will be familiar to you, and we will introduce also new methods to help you into calculating the integral of a function. So first, the chapter objectives is to recognize Newton-Cotes integration that is based on simplifying a complicated function or tabulated data into easy to integrate polynomials. Now, we should know how to implement trapezoidal rule, Simpson's 1/3 rule, and Simpson's 3/8 rule, and know how to implement a composite version of trapezoidal rule and Simpson's 1/3 rule. And finally, we should recognize that even segment odd points formulas, like Simpson's rule, achieve higher than expected accuracy. So maybe some terms are new for you here, but at the end of this chapter, you will be familiar with all of these new terms. So to start with, before going over the numerical methods, let us see the main applications of integration. You know that integration has a lot of applications. So for example, if you remember the example of reserves of oil, if you are interested into calculating the volume of reserves of oils, you know that this volume will be equal to, if you know the function, if you can find the expression of the function, it is equal to the integral of the function over this domain. Because when we have a 2D function, integral of x dx will give us the area under the curve. When we have a 3D function, then the integration will give us the volume under the curve. So it's of interest to know how to integrate a function to find the volume. And if it's a 2D function, and if it's 1D function, we can calculate area. So here, for example, if you have a wind blowing on a building, and you want to assess the total force, you need to know the total area of your building. So also here you can perform integration. Okay. Now, sometimes we have functions that are very complicated, such that we don't have analytical solution for their integral, or we don't have the analytical integration, or it's very hard to find it, and it requires very complicated mathematical tools. This is why, in some cases, developing numerical techniques will allow us to find the integral of a function without knowing the exact solution. So this is why we will develop several numerical techniques to perform the integration of a function. The main idea in Newton-Cotes formulas is that we replace a complicated mathematical function or tabulated data with an easy to integrate polynomial function. So the idea is that instead of dealing with a complex function of f of x, we replace it by a polynomial function that will be integrated. And let us see, we will start by the easiest case where we simulate a function by a linear function. Then we will consider quadratic function, etc. Yani, higher the order of polynomial you will use, you can expect to achieve better accuracy. So to start with, the easiest way is to use a linear function. Okay? So if I have the following function here, and I want to compute its integral, the integral of this function is equal to the area under this curve. So to benefit from this definition, we can say, let us approximate this function by a function which is simpler, for which it's easy to calculate the area. So the first rule that we can use is the trapezoidal rule, and I think that you are familiar with this rule. All you have to do, if you have a certain segment AB, you can take the extremity points, join them, and then you will simulate your curved function by a linear function. But here, as you can see, you will have a large error. So the error will be this area here. And as you can see, higher is the curvature of your function, higher will be your error. Because if this function was nearly linear in this interval, then you will get a very good computation when using trapezoidal rule. So higher is the order of your function. If it's highly nonlinear, the error will increase with trapezoidal rule. How we can go about this? To reduce this error, we can use more segments. Okay, because imagine here that instead of just 2 points, you consider 3 points. So I will divide then. So let us consider now. I will take this point here of my function, and first I will do the first interpolation will be between these two. So I will consider that I will interpolate function of x as linear function between these 2 points. And as you can see here, the error involved is very small, even negligible. Why? Because the profile of my function in this interval is nearly linear. This is why the estimated area is nearly equal to the actual one. This is why we said that when we have a function which behavior in a certain interval is close to the linear profile, the trapezoidal rule will work very well. Now, in the second interval, it is good, but of course the first interval is better. So in the second interval, I have more curvatures. F seconds is higher, but I was able to reduce my error a lot because I reduced the size of the interval. So now this is only my error compared to a very large error in the first case. So the main strategy when I want to use the trapezoidal rule is to increase the number of segments, because it will always help me. In general, it will always help me in reducing the error. And we will see why.
دكتور يعني بنعمل اثنين linear interpolation.
Yes, إذا 2 segments بتعمل 2, إذا 3 segments بتعمل 3, etc. It depends on the number of segments you select. Okay. Now, to consider, let us consider first not the composite trapezoidal. Yani when you take several segments, it's called composite trapezoidal method. Now we will just first derive a rule for the trapezoidal method with one segment, and when we will deduce what will be the rule for n segments. So if we just are considering one segment AB, then we can write f1 of x, we can interpolate it as a linear function. Hone, what is the technique we used by writing f1x as b1 plus b2 times x minus x1?
Newton.
Very good. This is Newton interpolation. Okay, so we use here Newton interpolation to interpolate our function, and it's a linear interpolation. So f1 of x can be written as f of a plus fb minus fa over b minus a times x minus a. Now, the integral will be equal to this area under the curve, and we know that the area of a trapezoid can be calculated as the base, which is this length here, times the average height. Okay, so here the base width is b minus a, and the average height is the small height plus the big height over 2. So this represents the width of my trapezoid, and this represents the average height, which is here an estimation of the mean function value, which is in the trapezoidal method the average, the normal average that we know, fa plus fb over 2. Okay, so now this is the general form to calculate the integral using a trapezoidal rule. Now, what will be the error involved in trapezoidal rule? So already we know that we will have an error because we are approximating a nonlinear function by a straight line linear function. Okay, and therefore we might have a very complicated nonlinear function, and we are just considering that we will approximate it as a linear function. So we expect that higher is the second derivative, higher will be the error. Because higher is the second derivative, then the profile will be far from the linear profile, more and more. And this is why we can expect that the error involved in trapezoidal rule should be proportional to f second of x. Because if f second of x is 0, this means that we have a linear variation, and then we will have a perfect match, then 0 error. If not, higher is the curvature, higher is the error. This is why we can understand now this mathematical formula. We are not responsible of how to derive it, but just we should understand the meaning of it. First, we can show mathematically that the error involved when calculating the integral using the following method, okay, is equal to minus 1 over 12 times the second derivative at xi at a certain xi which we don't know, but just we know that xi is between a and b, but we don't know where it is, times b minus a cubed. Since we don't know the location of xi, we cannot estimate exactly what is the true error, but we can put a certain maximum for it. Because if I know in this interval, if I know what is f second maxima, then I can say what is I can be sure that this error will be smaller or equal to minus 1 over 12 times f second maximum over b minus a cubed. Okay, so this will help me into finding a limit of my error. So what we can do, as we can see, the error is proportional to f second at a certain point and proportional to b minus a cubed. Since we cannot control this factor, the second derivative, which is property of the function, we can control the step size we take, and the interval width. So smaller is the interval width, smaller will be the error. This is why, as expected, as we did in our observation first, that if we use several segments, we can reduce the error. Okay? So this will be clarified more in this slide. So here we consider the following slide with different number of segments. So first, if we just use one segment, okay, here, it will be very bad. Because look, if you use just one segment here, this is the first point and this is the end point. Here, we will have a very large error because we have that the error is equal to this area. And we are not able to predict anything in this case because if we join the 2 points, we'll have x-axis. And this is not convenient because we'll have a maximum error here since the 2 points were on the x-axis. This is why here we should use several segments. If we start first by, in general, when we talk about composite trapezoidal rule, we divide into equal parts. Okay, you can tell me, why not dividing into different, different segments without equal part? You can do it, okay, but in order to develop a general formulation that is easy to calculate, we divide when defining the composite trapezoidal rule. We say that we should divide into equal segments, okay, because if we don't divide into equal segments, we will have then to do a separate calculation for each part. We cannot come up with a general rule. While here in the composite trapezoidal rule, we will see that we can develop a general rule depending on the number of segments we select, since all of these segments share the same width. Okay, so first here, let's say I want to enhance the accuracy of the trapezoidal rule. I will use the composite trapezoidal rule. The first possibility is to use 2 segments. So I will take a point in between. Then this will be my first linear segment, and this is my second one. As you can see here, in the first part, it's working very well. You know why? Because here you have a positive error, and here you have a negative error. So what will happen is that they will cancel out. So here in this part, you will have a good prediction of the integral, because nearly the area under the linear curve will be equal to a large, with a good accuracy, to the area under the curve, because the deviation here is positive, here is negative. So when you account for both plus and minus, will nearly cancel, or you will have reduced error. Now, in the second part, it's not working very well because I have large curvatures. I have large f-seconds, and this is why my error is significant in the second part. To reduce this, what I can do is to take more points. So now I will take 3 segments. 3 segments means 4 points. Always, the number of points is equal to the number of segments plus 1. Okay? So if I tell you I have 3 segments, then you will tell me then I need 4 points. Okay? So here I need 4 points, the extremity points, and 2 points in between. So now it will work much better. It's true that in the first interval, it's not much better because here I had the advantage of plus or minus, but I am comparing an overall. So this is the error here, which is acceptable. And in the second and third segments, the error is nearly very small. You know, this is the error here, this is the error here. So using 3 segments worked very well. I just have nearly this error, so which is much smaller than the total error obtained here by summing all errors. Now, I can see that higher is the number of segments, I am able to get better and better results. So now if I use 4 segments, so 5 points, also it will work in a good way. So here you have a positive deviation. Here you have a negative deviation, so they will nearly cancel out. And here it's working in a very good way. So the error will be reduced by using 4 segments. And higher is the number of segments. You can see here that it is working very well when I consider several segments. How many segments I have here? I count the point. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points means 8 segments. So with 8 segments, I was able to have a very good prediction of the integration. Now we can see this, we can understand this more in formulas, because we can demonstrate mathematically also an expression for the error, and we'll see it together now. So now, just for the composite trapezoidal rule, we should understand that we are dividing the interval AB into n equal intervals, and each interval is of a height b minus a over n. Okay, so each h for me is b minus e over n. And all I have to do is to apply the trapezoidal rule for each segment and then to sum the results I obtain. So for example here, if I want to use the composite trapezoidal rule to 5 segments, then I will have to compute first the integration for the first segment, which is the area under the first trapezoid, which is obtained by the formula we developed for single trapezoidal rule, which is the width, here the width is h, times fx0 plus fx1 over 2. This is the width, this is the mean between the average of the two values, which will give us the average height. We will repeat this procedure. So this is I1. This is the integral of part 1. We should add to it the area of part 2, I2, the area of part 3, I3, and all are calculated based on the same formula, which is the height times the average, so the width h times the average height. So you can see that I2 can be calculated as h times fx1 plus fx2 over 2. I3 is equal to fx2 h times fx2 plus fx3 over 2. I4 is equal to h times fx3 plus fx4 over 2. And I5 is h times fx4 plus fx5 over 2. What can you conclude here? Just the extreme points will appear one time in the summation, while any point in between will appear 2 times, because point x1 is common between the first segment and the second one, and point x2 is common between the second and the third segments. This is why you will have 2fx1 plus 2fx2 plus 2fx3 plus 2fx4. So you can generalize this result to say that if I want to use the composite trapezoidal rule for n segments, okay, then I will have the following result. I will have that I is equal to h times fx0 plus fx1 over 2 plus h times fx1 plus fx2 over 2, etc., plus h times fxn minus 1 plus fxn over 2. So to reduce this, the way of writing this in a more efficient way, I can write it as the width, which is b minus a over 2n. Why? Because you know that h is equal to what? H is, we can replace h by b minus a, which is the width of the whole interval, over the number of segments you are using. Okay? So higher the number of your segments, lower will be h. So h is equal to b minus a over n. So I can replace h in this formula by b minus a over n. And then I will have to take fx0 and fxn multiplied by 1, because they will appear once in my summation. while all other terms in between will have a coefficient of 2. This is why I can summarize this by saying that it's plus 2 times the summation from I equal 1 to n minus 1 of fxi, and of course over 2. So here they just took n inside of the brackets. So the result I is b minus a, which is the total width, times fx0 plus 2 times summation from 1 to n minus 1 fxi plus fxn over 2n. Let us try now together. We will do a problem on this to practice, but just before, as we have seen and expected, the error should decrease, okay? And mathematically, we can compute what is the expression of the error. So we can demonstrate mathematically that the error involved in this case will be equal to minus b minus a cubed over 12n squared times f-second bar. What do we mean by f-second bar? We have seen that for each interval, we can define the error, if you remember, as proportional to f-second at a certain psi I within the interval. And mathematically, we can demonstrate that the true error, which will be involved when we do several segments, will be proportional to f-second bar, which can be calculated as the average value of all f-second psi I of all segments. And if you define for each segment now, you are doing a certain interpolation, okay? You do linear interpolation, you have a certain error. In each segment, the error involved will be proportional to f-second at a certain position that we don't know, but we are sure that it is in the interval. So we can demonstrate mathematically that when we do n segments, the error obtained will be proportional to f-second bar, which can be found as the average of f-second psi I for each interval. Okay, and since we cannot play with this term, we don't have any tool to change it. Okay, what we can do just is to increase n. When we increase n, the error will be reduced. And as you can see, the error decreases quadratically with the number of segments, which is good. Okay, so we have a quadratic decrease of the error when increasing the number of segments. Let us see this in a numerical example. So let us evaluate the integral I using trapezoidal rule single application. So when they say using trapezoidal rule single application, this means that I just use one segment. I don't divide into several segments. So if I want to do this, all I have to do is to apply the formula. So here I just have these 2 points, 0 and 0.8. And since they gave me the actual function, I can predict the exact value of the true value. So first I can find I true to compare with my numerical calculation of the integral. So to calculate I true, all I have to do is to integrate the function given. It's a very simple function. It's a polynomial function. I can integrate it easily. So I have 0.2x plus 25 over 2x squared minus 200 over 3x cubed plus 675 x4 over 4 minus 900 x5 over 5 and plus 400 x6 over 6. Okay, and I compute this integral between 0 and 0.8. So now I have the exact value, and I want to, which will be equal to 1.6405. I want to compare with the numerical value of I obtained using trapezoidal rule single application. So I just have to take one segment, and B will be 0.8, and A will be 0. So all I have to do now is to replace 0 and 0.8 in my function here to get what is f of 0 and what is f of 0.8. And then I can compute that I is equal to 0.1728. And as expected, this will give me a very bad result with a true a relative error of nearly 90%. Why I can expect that I will have such large error here? I have two reasons. What are these two reasons?
It's high degree.
Very good. First, the function is highly nonlinear. Second, my interval, my segment is not small, 0.8. So I expect to have a bad result. So now to enhance my prediction, I can try to increase the number of segments. So now I will use the composite trapezoidal method. First, I will use a number n equal 2 of segments. So if I do this, I need 3 data points. So since my interval is 0.8, and always we use segments of equal length, then we can say that each segment will be 0.8 over 2, which is 0.4. So now I should add a point at the middle, and x of it will be x of, so this is x0. Now x1 will be 0.4, and x2 will be the extreme point is 0.8. And now I will apply my rule for n equal to, okay? So for n equal to, we can write the integral as b minus a times fx0 plus 2fx1 plus fx2 over 2n, and replace n by 2, okay? And then I will get a value that is much closer to the true value. And if I calculate the true relative error, I can see a very large decrease. So from 90% to 35%, which is expected because I increase the number of segments. But still, it's a large error. So to reduce it more, I need to take a higher number of segments. So now let us try to take 3 segments. If I have 3 segments, the length of each segment will be 0.8, which is the total width, over 3, which is 2.6